right here. So it appears that on average, both of them are speeding, yes? It does appear on average they're both speeding. Which one is more evidence of speeding, neighbor or police? Why neighbor?
It's a larger sample.
It's a larger sample. It's almost, if you look at the two data sets, they almost look the same as far as an average goes, don't they? If I had to guess, if you had to guess right now, ballpark it, what's the average speed of the neighbor data? If you had to ballpark a number right now.
It's 32 and a half miles.
32 and a half? I would lean a little bit more towards 35. Only Karen, because,
I entered the data and I...
did you use the frequencies too?
Yeah, 1 bar stat.
Oh, with the L1 and L2.
Yeah.
See, I would go a little bit higher because it's either 30 to 27. I feels like they're pulling this way a little bit, but
They're
it's
actually-
exactly 32 and a half.
They're both 32 and a half.
They come out exactly the same. Okay, good. I was thinking they go, this is why we have machines, I guess, because my gut doesn't always shoot us the correct.
Well, because I split it in half. I took the 15 and did...
Love
17.
it. Well, let's do this, friends. Let's do this. Let's get the data entered, and then we're going to create ourselves some hypotheses over here on the side board. So I'm going to go in L1, and I'm going to do exactly what Karen did, 17 and a half.
22 and a half.
Yup.
27 and a half.
Remember this trick from 243? You got to do the whole split down the middle.
Oops, you put
Oops.
in 73.
42 and a half. Whoops. Not quite that fast. 47 and a half. And then I'm going to put the neighbors in L2 and the cops in L3, if that's okay with you guys. 5, 9, 11, 30, 7, 0, 1. 1, 3, 2, 4, 4, 0, and 1. And you read 1 bar stats, is that what you said, Karen?
Yeah.
Awesome. Very, very nice, my friends. So we're attacking this 243-ish lead right now, if you will, 243-ish lead. So there's my neighbors data, cops data. Neighbors, cops. And I have not discussed the accuracy of this data. Michael asked a great question, or Christina, one of these two guys asked a great question. Do we have accuracy in this data? Again, let's assume the data we've got is good. Assume they measured it properly, somewhat scientifically. Okay, so let's do some 243. Let's do 1 bar stats on L1 and L2. There's your average, about 32 miles an hour. It's slight. This is the neighbors.
I missed a spot. Yeah.
That's okay. That's all right. Here's the average of the neighbors. So the neighbors average are 31.6, so roughly 32 miles an hour. Quite a big plus or minus. 6 miles an hour. Okay, but again, remember, this is descriptive statistics. This is the sample average and the sample standard deviation. We have not adjusted this for any kind of inferential study. This needs to be turned into a standard error. That's the whole point of 244 is this is fantastic. This is fantastic, but it doesn't give us any idea of if this is representative of the population. Now, let's look at the COPS data, which would be L1, L3, right? L1, L3. There's the COPS data. I mean, it's a little bit slower, yeah, on average. Almost the same, and a little bit wider standard deviation, a smidge. I would call those about the same. So if you look at both those data sets, both kind of look the same. They both average around 31 or 32 miles an hour, which is arguably not that high above 30, right? And they both have a pretty wide plus or minus, which indicates a little bit of skew. So my first question is, maybe I've got an outlier or two pulling things. Can I do a real quick graphical check to make sure there's no outliers? Is that okay with you guys? Is that fair? So what I'm going to do this time, I'm going to save myself the bell curves, save myself the histograms, and I'm going to turn plot 1 on with the neighbors data. Okay, see what I did there? Plot 1 is still a modified box plot, but we're looking at the neighbors L1, L2. And I'll turn plot 2 on with a modified box plot and analyze L1, L3 and see if it has any outliers. Because what I'm trying to see now is, are there exceptionally low speeds pulling the average down? My gut was leaning towards the speeds were a little bit above average significantly. It could just be my gut. I mean, I had breakfast not that long ago. It could just be churning in there. Who knows? A little yogurt, granola. So I'm going to turn plot 2 on now. Modified, L1, L3. Is everybody solid with me using L1 in both? That's my data. I'm using the same data. I'm just using different frequencies for each. Okie doke. Let's take a little zoom 9. Oh, there's my data. Let me see which one's which. I think the cops are on top. No, that's the neighbors up top. So here are the neighbors data. Here are the cops data. Essentially the same median, same upper quartile, same maxes. A little bit of a difference here. More variation in the lower, in the 25 to 50th percentile range than there is in the neighbor's data. So essentially, I'm getting roughly the exact same data set for both of these reports. So the question is, yes, descriptively, they're showing me the exact same thing. But inferentially, do they show me anything different? That's the question. Once we turn these data into inferential tools, this is pure descriptive, right? This is looking at this and only looking at this, not making it stand for the population. Let's wander over to here, friends. Let's wander over to here and define our variable. We're going to be testing mu, correct? What is the average that we're interested in testing? Well, good, it's 30 miles an hour. Yes, it's 30 miles an hour. But what's it standing for? Speed of the cars on this road. And what are we really interested to see if these cars are doing? Speeding. So we're really interested in this. So as Bob correctly surmised before, this technically should be a less than or equal to. Right? It should be a less than or equal to. I'm going to leave it as equal just because that's convention. But you're correct in putting less than or equals to if the opposite of greater than. Nothing wrong with that. Cool. There's our research hypothesis. That's our research hypothesis. This is our conclusion based on that. So, does it appear they're speeding or does it not appear that they're speeding? I propose we test both sets of data, the neighbors and the cops, and see if either one suggests that they're actually speeding. It doesn't look like on average they're that much above, 1 to 2 miles an hour, but this will give us like a hardline T test statistic standard deviation. So, let's test it. So what we'll do two. We'll have T for the neighbors, and then we'll also have T for the cops. And then we'll have P for the neighbors, and we'll have P for the cops. Let's test the neighbors first. T-test, yes. Data, Mu naught. What's mu naught going to be? 30 miles an hour, beautiful. List, yes. Your list is L1 for sure. Your frequency? L2. That's what your neighbor frequencies are, right? L2? Yes. Are they exceeding? I don't know. Let's find out. If they are, we're going to see it. Here comes our slow T curve. We're going to start seeing some area over there, if there is any. Oh, there's a little bit. Okay. So that's our test statistic for the neighbors. 2.44. 2.44 what? Yes. Is that significant? Is that significantly above average? Don't look at me, look at the p-value. What's the p-value?
Less than 8.
Yes, it is less than 5%. You can call it 0.00, 0.01, 0.009, whatever you want to call it. I'm going to put this less than 5%. Which means we are no longer in the confidence interval for 30 miles an hour. We are now more likely in a confidence interval above 30 miles an hour. Now, Christian's going to say, go ahead.
And you were testing greater?
We were testing, exceeding. So what this makes us look, this looks like there should be a curve over here that we're a part of versus the null curve around 30. Now, what I'm not saying how much more. I'm just saying significantly greater, okay? Make sure you're getting that. The confidence interval would give us how much more. This is just saying it's greater. So, I'm going to put, it appears, for the neighbors. The neighbors' data, it sure appears that the cars are exceeding, on average, the 30 mile an hour speed limit. Does the cops' data show that? I don't know. Let's go see. There's the neighbors. Rerun the test on L1 and L3. Everything's the same, but change L2 to L3. Christian, go ahead.
What is the highlighted portion represent on the graph?
Oh, that's the actual area, that's your p-value. That's the percentage of the curve that's being... Let me grab this one and show it to you in context, Christian. Great question. Okay, let's draw it. Here we go. Oh, before I go anywhere, let me pause this. Do you think there will be more or less or the same shaded right now?
More.
Okay, for most for more? Good. For most for more? Good. I agree with that. Why would there be more shaded?
Because the sample size is smaller.
Because the sample size is smaller,
And therefore there's more.
which means, you guys are awesome. The sample size is smaller, which means the curve is shorter and wider, which means the same location is going to generate more area. So you got to remember that these two data sets had essentially the same average. They did, about 32 miles an hour, 31, 32, arguably the same average, and arguably the same standard deviation. But the difference is that the neighbor's data curve did something like that over the middle of the line. Did something along those lines, which means that the neighbor's data curve had very little area out to the right. This shade that's here, Christian, this is where your test statistic falls. So in other words, the test statistic for this one is 0.57. So the COPS test statistic is only 0.57 of a standard deviation. It's still above. They're still speeding.
So is that saying that the value, I don't get, so what is this? Sorry.
What is the test statistic, friends? It's a number of standard deviations from average. If you're at average, you don't deviate at all. But we have a margin of error around that average that says you can go as far as this. If you go past that, you're now too far. You're no longer in our interval. A 0.57, this tells us right here, we're still in the interval. We've got a 29% chance. We've got a 29% chance. Oops, a 29% chance, assuming that the cars are going 30, that we got the data that we did. That's a huge chance. And I say huge, I'm comparing it to 5%. It's above 5%. 29% chance. There's plenty of agreement between the assumption that they're going 30 and the data that we got. Plenty of agreement, which means no contradiction, which means the COPS data, right, the COPS data does not appear to show cars speeding. The COPS data does it and the neighbor's data doesn't. You see the difference? And Jared, you nailed it over there. It's because of the sample size difference. They have exactly the same sensor and almost exactly the same spread when you look at it descriptively. But you apply that to the overall population, the neighbor's data is a better indicator of the population because you saw it more frequently. You saw it more frequently. Does that make sense? Ish? Susie?
So in the p-value, do we put what the actual p-value is, or just whether
Your
it's
call.
greater than or
Your
less
call.
than?
Your call. You can put less than, greater than 5%, or the actual thing. Sometimes I mix and match it a little bit. Because research journals mix and match it. Sometimes you do less than 5, sometimes you do the actual p-value. Some folks like if they have a very, very small one, they'll call it equal to 0, which is fair, it rounds to 0 in most cases. Watch this. Check this out. Let's do one more quick one informally here. Let's combine the data. Put the COPS and the neighbors together, shall we? We'll go over here at L4. Whoops. And I'm going to do L4. I'll do this relatively quickly. If you want to see how I do this, we're going to play with this kind of math more on Thursday with the stopwatches. I'm going to do L2 plus L3 in L4. So what I did was I put the blinker up on top and then typed in L2 plus L3. And when you press enter, it just combines the two data sets together. We'll do more of that on Thursday with the stopwatches, I promise, I promise. You can use these like spreadsheets in a lot of ways, which is pretty rad. Okay? So now we're going to test L1, L4. What do you think's going to happen? What do you think's going to happen when we test L1 and L4? Compare it to this. Tell me about the test statistic. What do you think the test statistic's going to be? Say that again. Dig it. It's going to be, what's going to be smaller? That guy's going to be smaller because where's that going to go? It's probably going to go even further away from average because it's more evidence they're speeding. Watch.
6.5.
Good, good. Watch this, friends. Data, everything's cool except L1, L4. All right, let's draw it. Here it comes. Looks the same. Looks the same so far. Looks the same so far. This is good. Uh-huh. Wait a minute. Same as it was before. That's exact. Is it exactly the same as it was? No, it's down. It's not down. It's not down as much as I thought it was going to be. But it's down from what it was before. You guys were right. You guys, I was wrong. I thought it was actually going to go up because I thought it was more evidence of it speeding, which means it would get further away from average. My apologies. I was completely wrong about that one. Go ahead, Bob.
Well, when you combine the two, shouldn't it, I mean, that's going to, if the p-value of 1 is lower, it's going to bring the other one down.
Well, you're applying a linear argument to it. I was assuming that since both data sets were showing they were speeding, combined, it was gonna show even more that they're speeding, but I guess the cops wasn't showing, it was a slight difference, the cops wasn't showing it was speeding as much as the neighbors. Damn! I hate that, I thought it was gonna be much more impressive. Oh well.
We should be able to-
Regardless,
Accelerate.
regardless, still significant, because your data set is larger, which is not as significant as I was hoping it would be. Cool? So, don't worry about t-tests on Thursday for sure. Don't worry about t-tests on Thursday. But the conclusions and what the conclusions mean and the types of error, that's all the same. The only difference is in step 2 and step 3. That's the only difference, is in step 2 and step 3. You're going to go to t-test instead of one prop. See, everything else is the same. Everything else is the same. Cool? Yeah? All right. We'll catch you guys then. Email